Welcome to this presentation on the properties of region of convergence. Because Z transform is an infinitely long sequence, we need to derive the following important properties. Poles of a stable system lie inside unit circle. Causal systems have larger degree denominator polynomials. These are fundamental properties based on the definition of Z transform. These are not derived properties. One does not need the concept of inverse Z transform to prove these properties. So let us take up property 1. Recall that ROC stands for region of convergence. ROC consists of a ring centered around the origin. What do we mean by that? Let us take a ring. This Z0 belongs to ROC. The magnitude is, say, Z0 absolute. Let us take a circle. Then all points on this circle have the same magnitude. So let us take an arbitrary Z. This Z will also belong to this region of convergence. That is what we want to prove. So here is the proof. Let us recall what Z transform means. It is given by this summation. Now Z0 belongs to ROC means this infinite sum of absolute values is bounded. So let us write it as follows. Let us start with this. Z0 belongs to region of convergence. So this absolute sum is bounded. I will write it like this, where I have taken a Z0 term separately, and then I will take this power outside. Now I will consider all Z such that their magnitude equals the magnitude of Z0. I will replace with this. So in the place of Z0 I have put Z, and I take this inside, minus n inside, and take it inside. I get this. So this is nothing but the Z transform of U of Z. See this expression? It is nothing but this. And we have got that this converges absolutely, because this infinity sign is greater than all of this. So we say that infinity is greater than this, or this absolute sum is bounded. In other words, arbitrary Z on the circle also belongs to the region of convergence, because it is given that Z0 belongs to region of convergence. So we have shown that every point on this circle belongs to the region of convergence. This is property 1. ROC consists of a ring centered around the origin. To prove the next property, we need this important fact. You might already know this, poles and zeros of a transfer function. Let us consider an LTI system with impulse response g of n. Its Z transform Gz is the transfer function. In general, g of z is given as nz by dz is a ratio of polynomials. Roots of n of z equals 0 are known as the zeros of the transfer function. Similarly, poles, which are nothing but roots of dz equals 0. Suppose Z0 is a pole, and if you substitute z equals Z0, what will happen? G of Z0 is unbounded, because d of Z0 becomes 0, because that is how the pole is defined. As a result, we conclude that this transfer function g of z becomes unbounded at its pole. Remember, the roots of d of z equals 0 are known as the poles of the transfer function g of z. So at the pole, the transfer function becomes unbounded. We need this result for the next property of region of convergence. So what is the second property? Poles are outside the region of convergence. In other words, ROC does not have any pole. How do we say that? At a pole, the transfer function becomes infinite, it is unbounded, hence does not converge. So a pole does not belong to region of convergence. It is straightforward. Poles are outside region of convergence because at the pole the transfer function becomes infinite. The third property is larger circles are in ROC for causal sequences. What does it mean? Suppose UN is a causal sequence, let Z0 belong to region of convergence, so it belongs to one circle, it is on one circle. Let us consider a larger circle. Now what happens? To prove all Z such that Z greater than Z0 will belong to region of convergence. Because this Z0 belongs to region of convergence, this circle belongs to region of convergence, this is what we called as the ring earlier. It is a circle whose radius is larger than the radius of this inner circle. What we claim is this larger circle will also belong to region of convergence if it is a causal sequence. How do we show this? Okay, we will apply the meaning of Z transform. It is given that at Z0 this sum is bounded. So once again we will write it separately. We will take out Z0, then we will take this Z0 to the denominator, and now we will use the fact that this magnitude is greater than the magnitude of this, and hence it is greater because this Z is in the denominator. Now we take it back, we get this is nothing but U of Z. So we have shown that this sum when evaluated at this Z, which is greater than the magnitude of this Z0, is smaller than infinity. Remember, all these are bounded and this is smaller than this, so obviously this is also smaller than infinity. In other words, this is bounded. So arbitrary Z such that absolute Z greater than absolute Z0 will also belong to region of convergence. So in other words, we say the larger circles are in region of convergence for causal sequences. Remember that this is applicable only for causal sequences or one-sided sequences. This is property 3. Let us go to the next property, region of convergence, property 4. Poles of causal, bounded input, bounded output, stable systems are inside unit circle. Recall this abbreviation BIBO, we saw it earlier, and in fact that gave rise to this condition, namely absolute sum of the impulse response is bounded. We derived this in fact in one of the earlier videos. Now we want to show that when we are given sequence like this, that is we are given a system that is bounded, BIBO stable, in other words this absolute sum is bounded, then we have to show that if we take the Z transform of this G of n, its poles will be inside the unit circle. Let us prove this. Because the system is causal, that is we take the sum from n equals 0 onwards, we do not need to consider all terms starting from minus infinity, it is enough if we consider n equals 0 onwards, because that is the definition of a causal system. So we have this condition infinity is greater than this, and this is nothing but this absolute sum with Z evaluated at 1. Okay. When we evaluate this sum at z equals 1, we get this. And what is this? If you leave out this z equals 1, this is nothing but absolute convergence of Z transform. So we say that absolute Z equals 1, that is unit circle, belongs to the region of convergence. As it is causal, larger circles belong to the region of convergence. We showed it in the previous property, and poles cannot be as a part of region of convergence. So poles have to be on or outside unit circle, because this is the region of convergence. So poles must be inside the region of convergence. So let us summarize. Unit circle belongs to region of convergence, larger circles belong to region of convergence. So the entire region on and outside the unit circle belong to the region of convergence. Poles cannot belong to the region of convergence, so the poles have to be inside unit circle if the system is causal and BIBO stable. This is a very important property. In fact, we will give some examples. So let us take G1 of n as 0.5 to the power 1 of n. When we take Z transform, we will get this. I would want you to do this calculation and verify that we indeed get this. G1 is bounded. As n goes to infinity, it is 0.5 to the power infinity, it becomes 0. So we say that G1 is bounded. And where are the poles? The pole is at Z equals 0.5 and it is inside the unit circle. So G1 is stable, it has a pole inside the unit circle. The pole is at 0.5. So let us take another example of an unstable system. Let us say 2 power n into 1 of n. Its Z transform is Z over Z minus 2. This is an unbounded sequence, because if you put n equals 2 to the power infinity is unbounded. And G2 is unstable, it has a pole outside Z equals 1, outside the unit circle. Notice that I am using causal sequence here and also causal sequence here. This G1 and G2 are impulse responses of causal systems. Poles of causal stable systems are inside unit circle. We will work only with causal systems in this course. So we say that the poles of stable system are inside or simply in unit circle. It is understood the moment we say that they are stable, they are inside the unit circle. They are not on the unit circle, they are not outside the unit circle. They are inside the unit circle. So in this course, we will design controllers that will make closed loop systems stable. So that is why this property is extremely important. We will come to the last property, region of convergence, property 5. Z transform of a causal signal is proper. So let us take U of k, let us take it to be a causal sequence. Its Z transform is U of Z, ratio of polynomials. Let us say that nz is a polynomial of degree n, dz is a polynomial of degree m. So we will prove that n is less than or equal to m. That is the meaning of this transfer function being proper. Okay. What is the proof? Proof is straightforward. Because U is causal, by property 3, larger circles belong to the region of convergence. As a result, the circle of infinite radius also belongs to the region of convergence. So infinity is in the region of convergence. In other words, if you put Z equals infinity, it should be bounded. So n is less than or equal to m. Otherwise, suppose this degree is greater than this degree and you substitute Z equals infinity, this will be unbounded. this will diverge at infinity. So we say that Z transform of a causal signal is proper, that is the denominator of degree equal to or greater than the degree of n. So all these are fundamental properties of region of convergence. Let us give an example of this. We will take the same G1 and we see that G1Z is causal, its numerator degree is less than or equal to denominator degree. Let us take another example, G3 of Z given by Z squared, and we see that the numerator degree is 2, the denominator degree is 1, it is non-causal. Alright, we will consider an example of causal systems later. We will show when we have a causal system like this, how to express them as a linear time invariant system. We will see that later. We will conclude this presentation by stating some important facts about the property of causality. We would want our controllers to be causal, otherwise they cannot be implemented. We check the causality of a controller through the degrees of its numerator and denominator polynomials. In fact, we would prefer design processes that ensure this degree condition. We will discuss this later in this course. With this, we come to the end of this presentation. Thanks for joining. Goodbye.